This module and the next one are all about one of my favorite conservation drainage practices, denitrifying bioreactors. The learning objective for this first lesson is to start to understand what bioreactors are and how they clean nitrate from water. The simplest definition for a bioreactor is that it is a wood chip-filled pit that cleans nitrate from water, in our case, drainage water. And the best way to get an understanding of what a bioreactor is to see one being built. So we'll look at a few examples. This first one is one of the smallest bioreactors we monitored in Illinois, at about 32 feet long by about 6 to 10 feet wide. This next bioreactor had a similarly small drainage area of about 17 acres, but it was slightly larger at 50 feet long by 12 feet wide. There is some nuance to the design process based on not just the drainage area, but also the slope and the diameter of the tile pipe. This next bioreactor treated one of our larger drainage areas at about 50 acres, but you see the dimensions weren't all that different from what I've shown you. Again, there's some nuance to the design process. One of our largest bioreactors was 76 feet long by 19 feet wide. Once you're done with construction, you can leave the wood chips open to the air, uncovered, or the top can be covered with soil, which can be seeded. As of right now, this is just really landowner preference. I like the out of sight, out of mind appearance of a covered bioreactor, but this is also harder to recharge with new wood chips. You saw those bioreactors all appear relatively long and skinny. The surface footprint of some of those are illustrated on the left of the screen. These were designed by the NRCS according to the Conservation Practice Standard Code 605, which we'll talk about during this module. But I also want to show you the layouts of the bioreactors on the right in the gray, just to plant the seed that there are different approaches to layout and design, especially when you look at what's being done for bioreactor research and when you look at bioreactors being built around the world. They're not all just long and skinny. Coming back to our basic definition, the next natural thing is to discuss how exactly do these pits full of wood chips clean water. So I'm going to go a little deeper with the definition, and we're going to talk through each component required for this water cleaning process. Firstly, you'll note we describe bioreactors as an enhanced denitrification technology. Denitrification is a natural part of the nitrogen cycle where, for example, nitrate in the soil is converted into nitrogen gas. This process is done by denitrifying bacteria in the soil, or in our case, denitrifying bacteria inside a bioreactor. The process of denitrification is exactly how wetlands clean nitrate from water too. It's the same process. Chemically, heterotrophic denitrification is a redox reaction involving the reduction of nitrate and the oxidation of carbon as the electron donor. This reaction is actually a multi-step reduction of nitrate into nitrite, nitric oxide, nitrous oxide, and finally dinitrogen gas if the process is complete. The final product is dinitrogen gas, which is a stable, non-reactive gas that is not a greenhouse gas. There are 4 key components to be able to have denitrification occur in a wood chip bioreactor. If any one of these 4 boxes is missing, you won't get much nitrate removal in your bioreactor. Starting with the solid carbon part. The wood chips serve as a carbon source to fuel this redox reaction of denitrification. And the wood chips are also thought to serve as a colonization surface area for the denitrifying bacteria. I'll point out when I say solid organic carbon, we nearly always mean wood chips, but in fact any organic form of carbon could work. We use wood chips to provide that carbon, but also to provide longevity of the carbon source. The most common question that I get about bioreactors is, does the type of wood chip matter? And the answer is so interesting that I have made that its own video coming up later. So let's talk about those bacteria next. The denitrifying bacteria that are the workhorses of this process are naturally present, meaning that denitrification starts happening on its own. I don't think it's exactly clear yet if the denitrifiers come from the soil or the tile drainage water or are already on the wood chips. But the reality is that this type of bacteria that do the denitrifying process are fairly ubiquitous or widely present, and they've always shown up on their own. Denitrification reactors used for municipal wastewater treatment take many months to grow the proper denitrifying bacteria to clean nitrate effectively from wastewater. So it's a little surprising and awesome, really, that wood chip bioreactors have never really had that same startup lag time. I also just want to reiterate that we call these wood chip trenches bioreactors because this is a biological process. It's the bacteria doing this work. The denitrifiers are the workhorses, and since they are a biological organism, it's called a bioreactor. We need to supply the denitrifiers not just carbon, but also nitrate. This is not a problem for our tile drainage water, for example. We did a review of the past 50 years of tile drainage studies to assess the nitrate concentrations that had been reported in those studies. And we found that the mean and median of more than 1,000 reported concentrations range from about 11 to about 13 milligrams nitrate nitrogen per liter. So, case in point, there is generally plenty of nitrate in our tile drainage. The last requirement for denitrification to happen is to have anoxic conditions. That means low oxygen conditions. If oxygen is present in the water, denitrification will not happen. The way we create the correct anoxic conditions in a bioreactor is by using the control structures. So let's walk through how those work to route the water correctly. This illustration shows just one potential layout, but nevertheless, starting at the upper left corner, water flows from the field underground in the drainage main pipe. The first part of the bioreactor that the water sees is the inflow control structure. This inflow control structure does two things, or it has two purposes. Firstly, this control structure provides a check dam, so to speak, to route water sideways into the bioreactor. The second important thing this control structure does is to allow bypass flow when there's a lot of drainage water leaving the field. Bypass flow means that water doesn't go through the bioreactor, but rather goes straight to the outlet or straight to the creek. It does not get treated in the bioreactor. This is an important design detail because in the US, we do not design bioreactors to treat 100% of the drainage flow to avoid the risk of backing drainage water up in the field. When those tile pipes are flowing full, that would be too much water too quickly to force into the wood chips. The ability for water to bypass is an important bioreactor design consideration for landowners who have invested a lot of money for their drainage systems. We do not want to significantly back up drainage water. Moving on, that water that does get routed into the bioreactor due to that first control structure moves through the wood chips. But as I mentioned, the trick here is that we need anoxic or low oxygen conditions for denitrification to occur. The tile drainage water naturally has dissolved oxygen in it, so this is where that second control structure comes in. This outlet control structure or outflow control structure holds water in the wood chips long enough for the dissolved oxygen to get consumed by natural aerobic microbes, which then allow the anoxic denitrifiers to get to work. But that dissolved oxygen has to be removed first. In other words, the second control structure creates a saturated depth in the wood chips and allows us to manage for a sufficient hydraulic retention time for denitrification to occur. You can see in this small model bioreactor flow coming from the left of the screen in through the inflow control structure, which also allows a bypass option for flow. The treated water moves through the wood chips, and the water level in the bioreactor can be managed using the outflow control structure. Also in this model, you can actually manipulate the stop logs to illustrate bioreactor management by pushing an additional stop log down in the inflow structure and increasing the check dam height, which means bypass won't occur until more water is built up behind that, now higher height of stop logs. This also increases the head, or the water gradient, across the bioreactor. You can also use the stop logs in the outflow control structure to manage the water level in the wood chips. That's it. We'll see you next time.